Thank you very much. Thank you for coming. Thank you for arranging for a wonderful day. I gather Chicago is like this 365 days in the year. The word human, my mentor, a man called Michael Day, would never let me use it without qualifying it. Do you mean an individual human being? Do you mean a member of the species Homo sapiens? Do you mean a member of the genus Homo? Or do you mean a member of the part of the tree of life that leads to modern humans? So he would never let me use it without some qualification. And of course, that means that I never let my students use it without some qualification, and it drives them mad. But I want to use the word human this evening in the sense of whether something is a member of the genus Homo. And in order to do that, I need to take you back to 1964. It was the year of the Civil Rights Act. This is one I couldn't resist. It was the year that the Beatles had songs that were in the top 5 of the Billboard top 40. It was the year that Elizabeth Taylor and Richard Burton got married for the first time. And it was the year that the Surgeon General issued a warning about the possibilities of a link between smoking and cancer. In other words, it was quite a long time ago. And in those days, these were the taxa that were recognized in the hominin fossil record. There were some African taxa, and there was Homo erectus that was mainly known from Asia. There was Homo rhodesiensis that was obviously an African taxon. There was a taxon called Homo helmii, and then Neanderthals and Heidelbergensis from Europe. So that was what I had to learn when I did a course on human evolution in those days. Just 1964 was just 5 years after the Leakeys had recovered a cranium that they called Nutcracker Man, or Zinjanthropus boisei. And that's a remarkable creature. You can see the cranium here, and you can see a strange molar tooth that they didn't know what it was until they found the cranium and thought maybe this strange molar tooth belongs to the creature that the cranium belongs to. And then in 1964, or at least on April 3rd, 1964, the oldest member of the genus Homo and the most primitive member of the genus Homo was Homo erectus, which was mainly known from Asia. Then, on April the 4th, 1964, this paper was published in Nature. And it says a new species of the genus Homo from Olduvai Gorge, from the same place that Zinjanthropus boisei have been found. And it was by Louis Leakey and a colleague of his who he had asked to describe that wonderful cranium from Zinjanthropus boisei, a man called Philip Tobias, and John Napier, who was a colleague of Bob's and mine in the University of London and a very distinguished primatologist. And what they did in that paper was that they revised the diagnosis of the genus Homo. So let me try and unpack that for you. They sort of redefined Homo. So what I want to do this evening is just to consider what led up to that proposal, because that was a pretty dramatic proposal. We're going to redefine the genus that all modern humans belong to, and we are suggesting that we are describing a new species, and and the basal species, the most primitive species in the genus Homo. So what led up to that was that the cranium Zinjanthropus boisei was called Olduvai hominid 5. Okay, you come from Chicago, so you must realize that Olduvai hominid 3 was discovered before Olduvai hominid 5, and Olduvai hominid 4 was discovered before Olduvai hominid 5. And Olduvai hominid 4 was a little sort of scraps of teeth that they really didn't sort of know what to do with. And while they were considering these, which they were extremely pleased to have, just a few weeks later, they discovered this cranium. So they, if you discover a cranium, you stop worrying about a couple of teeth. So they stopped worrying about a couple of teeth. And then they discovered OH6. I don't have my driving license for this machine. So they discovered OH6, which is just a few pieces of a cranium. And then they discovered a little more of a different cranium, and then a mandible here. And they began to realize that this was a creature that was unlike Zinjanthropus boisei. Zinjanthropus boisei is a creature with a flat, wide face, with a crest down the middle of the cranium, with huge teeth, huge molar teeth. This was a different sort of animal. Now, in 1959, when they found Zinjanthropus boisei, this was the first hominin they had found, which was the same age as the stone tools that they had been recovering. So they thought, Zinjanthropus boisei must be the maker of the stone tools. So Zinjanthropus boisei had a rather short career as the maker of the stone tools, because in 1964 they thought, this is a better candidate for the maker of the stone tools. Why was it a better candidate? Because it seemed to have a bigger brain. It seemed to have a bigger brain. And so they said to, Zinjanthropus boisei, sorry, we found a better, a more likely maker of the stone tools. And they also found the skeleton of a foot, and they interpreted the skeleton of the foot as being the skeleton of a striding biped. A striding biped. And you must realize that the authors, John Napier was a Brit, and in Britain, when we walk, we stride. I've always been struck by this notion that it's a striding biped. It's a stockbroker on the way to the stock exchange, or it's a banker on the way to the Bank of England. So it not only had a larger brain, it was interpreted as being a striding biped, and there were some hand bones, and they interpreted those hand bones as being dexterous, the hand of a dexterous creature. So they put all these inferences together, and so they called this creature Homo habilis, habile, capable of making things. And so they said, this was the creature that was making the tools. And they also had some other specimens, OH13, and they had this rather fragmented cranium, but a pretty reasonable, or at least pretty reasonable for 1.8 million years, set of teeth. So this was the material that they wrote about in this article in Nature. And there's Louis Leakey, who always had a grin on his face, and Philip Tobias, who has rather a questionable taste in sweaters, and John Napier. And these three people were the authors of the paper. The paper is called A New Species of the Genus Homo from Olduvai Gorge. So So on April the 4th, 1964, and the other thing that happened was that Olduvai Gorge wasn't just a source of fossils, it was also a place where new dating methods were tried out and were found to be successful. And so Olduvai Gorge, the material Homo habilis was dated, it was one of the first hominins to be dated using potassium argon dating, and it was one of the first hominids to be dating using what's called magnetostratigraphy. And so it had the surprising age of about 1.8 million years. So this was a sort of a double whammy. Okay, we found a new species of Homo, and it's 1.8 million years ago, by the way. Substantially older than anything that had been found before. So having confused you with all that information, I want to spend the rest of my time asking a question. So what is a genus? And which taxa should be included in our own genus Homo and why? And then when and where did the genus Homo begin? So I want to try and answer those questions. And in doing so, I'm going to draw on research of graduate students who were my graduate students in the past or who are current graduate students, Eve Boyle, Mark Collard, Andrew Dew, and David Patterson. So what is a genus? Well, this is something that Mark Collard and I thought long and hard about, and we thought you could just go to, any one of many evolution textbooks and there would be a nice sort of definition of the genus. Actually, it turned out that there were lots of definitions of the genus. So we had to sort of sort through all these definitions and use our own gray cells and say, well, what is a genus? And there were two criteria, it seemed to me. There were two criteria, it seemed to us. And the first was that the species needs to be in the same clade, also known as a monophyletic group, which I'm sure has helped you, as the type species of the prospective genus. And a clade, I will try and explain what that is using an analogy in a minute. So that converts into a definition, in other words, all of the taxa, no more and no less than that are descended from a recent common ancestor. So that's what a clade is. So I'm going to use, much to the amusement of my colleagues who think I'm obsessed with cars, which I'm not, I'm going to use the example of a make of car as an illustration of what a clade is. And the example I'm going to use is the Toyota Motor Company, which emerged from a company called Toyota that made equipment to manufacture material. And the Japanese had no car industry themselves. So they decided that the Toyota company should start to make cars. And they did. And this is the prototype of the first Toyota. This is the first car, and it was made in 1935. So that is the common ancestor of all Toyota cars. Okay? And we know because somebody's written the history of the Toyota Motor Company. And so it's the same as all of the taxa, no more or no less. In other words, you can't have a Nissan, okay? And you can't leave out any Toyotas because it's the whole 9 yards, it's the whole shooting match. And the recent common ancestor is the prototype car. The second criterion for a genus, we suggested that it needs to be the same grade. So what's a grade? So it's a clade is like a make of car. What's a grade? So it needs to be in the same grade. In other words, its way of living needs to be closer to, it's a group of animals that are doing more or less the same thing. disregard the mumbo-jumbo on the slide. So it's a group of taxa that shares a suite of adaptive features. In other words, all the members of a genus need to be in the same adaptive zone. So back to motor cars. One of the great successes of the Second World War was the Willis Jeep. And so the Japanese decided that they would make a Japanese version of this Jeep. So in 1951, instead of making passenger cars, they made a four-wheel drive vehicle, and it was called the BJ. So within the Toyota clade, there is a subgroup of Toyotas which are four-wheel drive vehicles. They can go places that two-wheel drive vehicles can't. And so they are a new adaptive grade, yet they're in the Toyota clade. And so I'm going to suggest to you that four-wheel drive Toyota vehicles are a good example of something that's equivalent to a genus. They're all sort of adaptively coherent, and they're all made by the same motor car company. And there are people who spend their life worrying about the history of four-wheel drive cars made by Toyota. And so here is a diagram of the evolution of four-wheel drive passenger vehicles made by Toyota. And I'm going to ask you, or at least suggest to you, that it's a good analogy for a genus. One of the reasons we need the Leakey Foundation is, of course, for the Toyota Motor Company, it's pretty easy because there are people who remember what happened. And the Toyota Motor Company has some historians who work for the Toyota Motor Company, so they record all these things. And there are people who have nothing better to do, who spend their time on the internet writing about the history of the Toyota Motor Company. I shouldn't say it because there may be somebody here who's an expert on the Toyota Motor Company, and it's a perfectly wonderful thing to do. And thank goodness people have done it, otherwise I couldn't do this. But our problem is that instead of this picture, we have to deal with this picture. In other words, we have to reconstruct the equivalent of the history of the Toyota Motor Company using little scraps of evidence. And there is nobody writing it down, and that's the challenge, and that's why paleoanthropology. And Bob Martin, I remember very well, I'm not sure whether it was in this rather mindless class about how to lecture, but in those days there was a sort of a category of hard sciences, things like chemistry and physics, and softer sciences, things like economics and things like that. And Bob said, you know, the problem is that we work in a difficult science. It's not hard, it's not soft, it's just really difficult because you're trying to recover evolutionary history and there's not a lot of evidence. So if a genus needs to be a clade and a grade, which taxa should be included in the genus Homo and why? Well, Homo sapiens is the type species of the genus Homo, even though there is no type specimen of Homo sapiens. But it's the type species. So that has to be included in the genus Homo. When Neanderthals were discovered, they were suggested that that species should be added to the genus Homo. So it's like sort of taking a modest-sized car and, you know, which looks like Homo sapiens, and then, you know, Neanderthals are different. They have different shaped cranium, different shaped teeth, but nonetheless, they sort of live their lives much like modern humans live their lives. So you're making the genus Homo a little more inclusive. It's a bit like having a tennis club, and you start with great aspirations that in order to belong to this tennis club, you have to, be this good at tennis, and then you discover there are only 9 people who are that good at tennis, and you realize that doesn't make for a very vibrant club. So you say, okay, we'll relax our criteria and we'll, let other people join. Then with the inclusion of what was Pithecanthropus erectus and Sinanthropus pekinensis into the genus Homo, Homo became even more inclusive. And so the criteria for joining the tennis club were relaxed even more. Can you hold a tennis racket? Do you know which bit to hold? Okay. So you relax the criteria a little more, but you still say it's a tennis club. So the situation in 1944 was that Homo erectus was the most primitive member of the genus Homo. Then with the proposal in 1964 that there was an even more primitive creature in the genus Homo, that relaxed the criteria even more. And the question I want to ask really in this lecture is, were those criteria relaxed more than they should have been? In other words, does the inclusion of Homo habilis in the genus Homo render the clade criterion mute, and does it render the grade criterion? In other words, does it sort of destroy the adaptive coherence of the genus Homo? So how did the 1964 proposal withstand the test of evidence? Because if you're a paleoanthropologist, you come up with a hypothesis. This is, how I think the world is organized and looks. And then people find more fossils, and those fossils are either consistent with your hypothesis or they're not, in which case your hypothesis bites the dust and somebody comes up with a different hypothesis. That's how this historical science works. So after 1964, the Leakeys found more specimens from Olduvai Gorge, which they thought were consistent with these new specimens belong to Homo habilis. They found an associated skeleton. Now, an associated skeleton is a specimen that preserves more than one element of the postcranial skeleton, as well as maybe some teeth or jaws. Now, the good news is that OH62 is an associated skeleton. There is a piece of humerus and some forearm bones and a bit of the femur and the proximal tibia. The bad news is that it's been in a serious road traffic accident. And so OH62 is really fragmented. The cranium is in lots of pieces. Lots of the teeth are in lots of pieces. So the good news is that it's an associated skeleton. The bad news is that it's a highly fragmented one. But nonetheless, that palate looks nothing like the palate of OH5, which is the type specimen of Zinjanthropus boisei. So that also probably belonged to Homo habilis. And then this is material that we were finding in northern Kenya, and this was also suggested that it might belong to Homo habilis. And then material was found from sites in southern Africa, and it was suggested that they also belong to Homo habilis. One of the jobs I was given as a member of the Kubifora research group was to try and make sense of all the cranial remains that were discovered at Kubifora, and this is the book that if you really can't sleep, this is the solution to your problems. And what I suggested was that it's most likely that the material that was discovered sampled not one, but two species, but what I suggested was that the Leakeys were probably right, Leakey, Tobias, and Napier were probably right, that even though there was some evidence that there were two species of Homo represented at Cubifora and in the Shungura Formation in the Omo, there was no evidence that there was more than one sort of early Homo at Olderby. So Homo habilis was good, and the question was, were the two species at Cubifora, was one of them Homo habilis, or were they two new species of early Homo? And if one of them was Homo habilis, what the hell was the other one? So, so how did this new evidence affect the clade and the grade definitions of a genus? Well, as far as the clade definitions of the genus, the new evidence made not that much difference. But as far as the grade criteria was concerned, Mark Collard and I suggested that the inclusion of habilis changed, sort of destroyed the adaptive coherence of Homo. And we set out the case for that in a paper in Science in 1999 called The Human Genus, imaginatively called The Human Genus. And what we did was to look at various criteria, things like body size and body shape and inferred locomotion and the size of the jaws and teeth and the rate of development and brain size. And basically, it's not surprising that Neanderthals get an H for Homo for all of those things. Homo heidelbergensis, there's not a lot of evidence, but there are some H's and one A for Australopithecus. Homo erectus gets H's, Homo ergaster gets H's, but Homo habilis got a lot of A's for Australopithecus. So we suggested that there was an argument to be made that Homo habilis should not be included in the genus Homo. It was a great idea at the time, but nonetheless, the years that had passed between 1964 and 1999, the hypothesis that habilis should be included in Homo, it seemed to us that it had been substantially weakened. What I need to say was that it seemed to us that it had been substantially weakened, but almost nobody took any notice of what we said. Even though I still think we were right, and I will try and persuade you that we were right. So we suggested that Homo, it was quite right to have stopped the tennis club, the performance relaxation at the bottom of Homo erectus. And so we suggested that the two species of early Homo should actually be included in Australopithecus as Australopithecus habilis and Australopithecus rudolfensis. But this went down like the proverbial lead balloon. So what has happened since 1999? Well, there's been more fossil evidence. And that's the sort of thing that the Leakey Foundation, that the funding from the Leakey Foundation allows to happen. And this is new fossil evidence from this jaw, from Cubifora, and then this maxilla. And basically the new fossil evidence, the good news for Bernard Wood was that the notion that there were two species in early Homo was consistent with this new fossil record, with this new fossil evidence. The bad news is that I might have got some of the allocations slightly wrong, okay? That maybe a jaw that I thought belonged to Homo rudolfensis may actually belong to Homo habilis. But in general, the news was, the balance of the news for me was good. That doesn't happen very often. The other thing that's happened since 1999 is that there has been a proposal that the genus Homo goes back in time to 2.8 million years on the basis of this mandible found from a site at Ledi Guraru in Ethiopia. So the other thing that's happened since 1999 is that, and And basically, what I do is analyze the fossils that other people find. And so what you need is more fossils, there's no doubt about that, but you need to get smarter at analyzing the fossils that you do find. There's no point in just finding more fossils and not developing methods. There's no point in developing methods if you don't find new fossils. You need both of those things. So there has been new evidence since 1999, new methods of really crawling all over the fossil evidence, trying to extract more and more information from it. And some of that new evidence involves inferences about body shape, some of it involves inferences about locomotion, some about cognition, some about dexterity, some about diet, and some about life history. The inferences about locomotion that have been made since 1999 really backed up what Mark Collard and I said, was that Homo habilis probably was not moving around in the same way that Homo erectus was. Homo erectus was an obligate biped. Homo habilis was capable of bipedalism, but it was using its arms a lot more than you and I do to move around as a biped. There was also some evidence which has come up about cognition. And of course, we don't know anything about the cognition of hominins that lived millions of years ago, but we make inferences about cognition based on their brain size. That's not, but that's what we do. Whether we should do that is another matter, but that's what we do. And basically, there's been some sort of conventional wisdom about brain size. And the conventional wisdom was that there was an increase in brain size that occurred about 1.8 million years ago, which coincided with the origin of the genus Homo if you included Homo habilis in the genus Homo. And so this diagram, which was in a paper by Leslie Aiello and Peter Wheeler, has become sort of iconic to the extent that now in textbooks, there is the genus Homo burst of increase in brain size at 1.8 million years. Now, like all conventional wisdom, you should suspect it. Okay? You should suspect it. And C.H. Waddington, he referred to conventional wisdom as the conventional wisdom of the dominant group, and his acronym really appeals to me. It's cow dung. Okay? Conventional wisdom of the dominant group. Always suspect conventional wisdom. So what I did was to get a group of bright graduate students that was led by Andrew Dew, who's now a postdoc at the University of Chicago. And so there are more data points. But of course, these are points. And we know that, if you're collecting information about something that's a couple of million years ago, one point would suggest that there is no error. And that's unlikely, because often the endocranial volume, the brain size, is extrapolated on the basis of a rather fragmentary cranium. And there is also some error in the date. So probably you shouldn't have these points. You should have a diagram that expresses the error that's involved in the measurement of the brain volume and the date. And when you do that, to cut a long story short, and you test those data against various evolutionary modes, random walk, gradualism, stasis, punctuated equilibrium, because this genus Homo burst was an example of of an event that's called a punctuation event in an otherwise equilibrium of brain size. And when these guys did that, they found that the data fitted far, 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 far better to a gradualism model than to an increase in brain size at 1.8 million years. So that weakened the case for the 1.8 million years. The other thing, this is another student, this is David Patterson's work, was looking at stable isotopes. And stable isotopes, you are what you eat. And you can, if you eat a lot of grass, you have high levels, you have levels which are called C4, okay. If you eat a lot of leaves, you have levels of stable isotope which is called C3. If you eat a mixture of grass and leaves, you're a mixed feeder, and so you're C3/C4. Okay. If you're a grazer, you're C4. If you're a browser like a giraffe, you're C3. If you're an antelope that both grazes and browses, you're a mixed feeder. You can look at these stable isotopes in the soil. So not in the bones of animals, but in the soil. And when you do that, you see that in Lake Turkana from 2 million years to about 1.3 million years, there isn't much of a trend. Okay? Stays more or less the same. Sort of wooded grassland signal, sort of equivalent signal. So what happens if you look at the isotopes in animals? From this, we would infer that there hasn't been a great deal of change in the environment. In other words, the animals, what they could eat was much the same at 2 million years as it was at 1.3 million years. So what happens if you look at the animals? Well, if you look at Paranthropus boisei, the early part of that time range is much the same as the later part of the time range. Paranthropus boisei is a C4 sort of type of animal, and it's C4 at 2 million years, and it's C4 at 1.3 million years. It doesn't change. Whereas if you look at Homo, the early ones are C3/C4, and the C4 signal becomes stronger in the later ones. These early ones are Homo habilis/Homo rudolfensis that we were suggesting should not be in Homo. The later ones are our early African Homo erectus, which we suggested was a perfectly good member of the genus Homo. So what might be the explanation for the change in the stable isotope? Well, we don't know. But one explanation is that this C4 sort of grassland signal is because Homo started to eat animals that were eating grass. Because you are what you eat. And if you eat meat of animals that are grass eaters, you inherit their grass signal. Now, we don't know that that's the explanation, but that's the explanation I would like it to be. What's interesting is that Homo is the only taxon that undergoes a significant enrichment in delta 13, in carbon delta 13, through time. All the other animals either stay the same or they become more C3, not C4. So, we think that's pretty good evidence that there is a shift between the way that Homo habilis was making its living and the way that Homo erectus, or early African Homo erectus, was making its living. So we think if there was a shift, it wasn't from Australopithecus to Homo habilis, because Homo habilis has a stable isotope signature which is like Australopithecus. It was a shift between Homo habilis and Homo erectus. So, you will be relieved to hear I'm getting to the bottom of this slide. So when did Homo originate? Well, we think it originated here and not there. But what you have to realize is that these columns, and this is a diagram that Bob was referred to, or at least an updated version of it, these columns are They represent a hypothesis about the existence of a taxon, and they represent a hypothesis about, well, not a hypothesis, they represent an observation about the first time we see that taxon in the fossil record and the last time we see that taxon in the fossil record. So the existence of the taxon is a hypothesis. The bottoms of those columns isn't a hypothesis, it's an observed fact. And the tops of those columns is not a hypothesis, it's an observed fact. The fact that that's a separate species is, of course, a hypothesis. So each column represents a hypothesis about the existence of a taxon and the ages of the existing site samples of that taxon. But the observed first and last appearance dates of a taxon are just that. They are not the first time that taxon walked on the Earth, or the top of the column is not, the last person standing of that taxon. So the column doesn't necessarily represent the beginning of the existence of the taxon, it just represents its appearance in our fossil record. So it's racingly certain that all the taxa in that diagram were around before the bottom of their column, and it's racingly certain they were all around subsequent to the top of the column. And there are different sorts of errors around the first appearance date and the last appearance date, depending on how many fossil sites there are, how many fossils were discovered at those fossil sites, and so on. So what the columns are not are take-to-the-bank statements about the timing of the origin and extinction of each taxon. I cannot emphasize that too much. So, for example, you can't say, oh, if the Leddy-Gararu mandible belongs to Homo, then Homo begins at 2.8 million years. I should say, not that you can't say it, because people do say it. I'm saying that you shouldn't say it. And so what I'm suggesting is that the origin of Homo is sometime before the earliest evidence for it. Likewise, if you think like us that Homo erectus is the earliest evidence of Homo, that's not the origin of the genus Homo, it's sometime before the earliest Homo erectus fossil. So the last question is, where did Homo originate? Well, what you have to realize is that Africa is a big place. I remember coming to the Field Museum a few years ago, and there was an exhibition about Africa. And they drew Africa on the floor of the hall, and they put other countries in Africa to show just how damn large Africa was. And the problem is that the projections of the world that you see in atlases, they systematically minimize the size of the countries closest to the equator. That's just the way these projections work. So, I was really impressed because in Africa was, Australia, North America, South America, Europe, it's a big place. Okay, Africa's a big place. And the fossil sites in Africa, the evidence for human evolution comes from sites in and around the Rift Valley and from a few sites here in the Dolomitic limestone in southern Africa and from sites in Central Africa. At the most, you can persuade yourself that that's 3.5% of the land surface of Africa. So if you think that we know everything about human evolution by discovering what was happening in parts of 3.5% of the surface of Africa, I'm sure anybody coming to this lecture would say, that's probably unlikely. Okay, that's really unlikely. And the problem is, it's the problem of the drunk and the keys. The drunk person has dropped their keys. Where do they look for their keys? They look for their keys under the lamppost. Not because that's where they drop their keys, because it's the only place you can see. And the only place we can see is the Rift Valley and the Dolomitic and the caves in the Dolomitic limestones. But that doesn't mean that's where the keys were dropped. And so you have to realize that we probably haven't sampled everything there is to know. So given we cannot know what data are missing, what should we say about the origin of Homo? The answer is as little as possible. Really, and I'm serious. I mean, as little as possible. And the origin of the genus Homo, like all origins-related questions, is challenging to answer scientifically. It doesn't mean it's not a legitimate question to ask, but if you're a scientist, you have to say, I can't do everything. You have a very interesting question, but I can't answer it scientifically. And our job is not to pretend that we can do things that we can't do. There are a lot of people around at the moment doing that in spades, and so we shouldn't sort of join them. So I want to thank you for coming this evening, and I just want to pay tribute to a colleague who died last year, Frank Brown, who was a geologist who worked in East Africa, and he was really intimately connected with the Leakey Foundation. And a lot of these columns, the heights of those columns and the dates and the information that goes into assembling those columns, it's due to Frank, and he's sadly missed. So thank you for coming, and thank you for your patience. I know some of you expected to be home or having your supper now, so thank you very much.